Today, we're diving into a really fascinating story from the front lines of AI research. It's about a tiny, elegant model that took on the biggest names in the industry, and, well, it won.
So can it? I mean, it sounds kind of impossible, right? In the world of AI, you hear it all the time, bigger is better. But what if that's not the whole picture? That question is really at the heart of what we're talking about today, and the answer, it might just change how you think about building smart machines.
All right, to really get this story, we first have to talk about the current champions of the AI world, and a surprising blind spot they all seem to share.
For years now, the main philosophy behind large language models, LLMs, has basically been scale is all you need. The thinking is, if you just throw enough data and a mind-boggling amount of computing power at a massive model, it'll eventually learn to do just about anything. And honestly, for a lot of things, that has worked amazingly well.
But here's the catch. It turns out when you give these huge models problems that need structured, step-by-step logical reasoning, think complex puzzles, they just fall apart. It's kind of like having a supercomputer that can write you a beautiful poem, but can't solve a basic riddle.
And I'm not just saying that. We have the cold, hard data. Just look at this chart. It shows how some of the most powerful AIs on the planet performed on a super difficult Sudoku test. And look at those bars. Models like DeepSeek R1 and Claude 3.7 are scoring a big fat 0. They literally cannot solve a single one.
So this was a pretty glaring weakness, right? And it got researchers thinking, okay, we need a totally new approach. Their first crack at it was really clever, but as you'll see, it was also incredibly complicated.
So, meet the Hierarchical Reasoning Model, or HRM. The idea here was, instead of one giant brain, why not use two smaller networks? They would basically pass information back and forth to each other, recursively getting closer and closer to the right answer. It was a completely different way to tackle the problem.
But different also meant, well, complex, super complex. HRM had two separate networks that were running at different speeds, and the whole design was justified with these really complicated arguments about how the human brain might work. And under the hood, it was leaning on some heavy-duty math, like the Implicit Function Theorem, just to get it to train properly. It did work better than the big LLMs, but man, it was a beast to understand.
And this is where our story really takes a sharp turn. A new group of researchers looked at the super complex HRM and asked a really simple question. What if we can make this better by making it simpler?
And that question led them to create the Tiny Recursive Model, TRM. The whole point wasn't to add more bells and whistles, but to strip them all away. You can see it right there in their paper. Their goal was a much simpler approach that could actually end up performing better.
And when you put the two side by side, the difference is just night and day. HRM used two networks. TRM uses just one. HRM had 27 million parameters. TRM gets by with only 7 million. And maybe most importantly, it throws out all the complex justifications and just replaces them with simple, clean logic.
So how on earth did they do it? What was the secret that made this tiny model so incredibly powerful? Let's take a look inside.
Okay, the genius here really comes down to 4 key simplifications. First, they just tossed out all that complex math. No more fixed-point theorems. Second, they completely reimagined what the different parts of the model were even doing. Third, they fused those two networks into one single unified network. And then, and this is the really wild part, they made that one network even smaller, just 2 layers instead of 4.
That reinterpretation step was the real lightbulb moment. Forget all the confusing brain analogies. In the TRM model, it's simple. It just has 2 jobs. Keep track of Y, which is its current best guess for the answer, and Z, which you can think of as its mental scratch pad, the reasoning it's using to get to that answer. It just loops back and forth, reason, then answer, then reason again, getting better each time. So simple, so elegant.
So all this radical simplification, did it actually work? Oh yeah, this is where we get to the knockout punch.
Remember that Sudoku dataset? The one where the biggest, most expensive AIs in the world scored a 0? TRM scored 87.4%. Just let that sink in for a second. That's not just a small improvement, that is a whole different league of performance. All from a model that's a tiny fraction of the size.
Looking at the direct comparison here is just, it's incredible. On Sudoku, you go from 0% for the giants, up to 55% for that complex HRM model, and then all the way up to over 87% for our little TRM. And it's the same story on another tough puzzle, maze pathfinding. TRM just blows the others away. And it's doing it with only 7 million parameters.
And to prove this wasn't just some lucky fluke, check out the results on ARC-AGI, which is known for being one of the hardest AI reasoning benchmarks out there. Our little 7 million parameter TRM doesn't just beat the 27 million parameter HRM, it also scores higher than Google's Gemini 2.5 Pro, a massive, state-of-the-art model.
So, what does all this mean? What's the moral of this incredible David and Goliath story for the world of AI?
Well, the really big takeaway here is that we might be a little too obsessed with scale. The success of this tiny model is a direct challenge to that whole bigger is always better idea that's been driving AI for years. It tells us there might be another, smarter path forward.
Ultimately, the lesson is really simple, but it's also profound. While all the giants were trying to solve these problems with pure brute force, a smaller, more thoughtfully designed model found a much smarter way to do it. It proves that elegant design can absolutely triumph over raw power.
And that leaves us with a really fascinating question for the future, doesn't it? We've just seen that for complex reasoning, a leaner, smarter approach wins. So, what other problems are we trying to solve with a sledgehammer when what we really need is a well-designed key? Definitely something to think about. Thanks for tuning in.